Hi class, we're on chapter 11.1 and 11.2. We're going to be looking at straws for 11.1 and the kinetic molecular theory in 11.2. So this whole section has to do with gases. So first section discusses a straw and how a straw works. Basically what happens is that a straw is open to the environment just like the glass is, and that means that the pressure inside the straw is equal to the pressure outside the straw. So it's open to the environment. However, when you drink through the straw, you create a pressure difference, meaning that the pressure inside the straw is lower than the pressure outside, and this creates a pressure difference of this being higher here, and it pushes the liquid through, which allows you to drink through a straw. So we're going to be looking at what pressure is. Pressure is a force exerted by a certain area by the gas molecules that they collide with the surface around them. So what this means is that as molecules keep colliding with the surface, they exert a pressure. And that pressure is what we're reading. So that's why when we have something that's very high pressure, think of like air in a bike. There's a lot of molecules and they're pushing against, they're colliding with the surface of the inside of that tire. And that results in the pressure that you feel because of course you want your wheel to be inflated. So here, a molecule exerts a force when it collides with the surface. The result of many of these collisions is the pressure. When you don't have a lot of molecules, let's say as in an example of the air in a bike, the tire's flat. But the more molecules you put in to the tire, they will collide more and more with the surface, and that will result in higher pressure and keeping that tire inflated. So at Earth, at sea level, the gas molecules in our atmosphere exert an average pressure of, let's just cut down to this one. This is Newton meter squared. This is 14.7 pounds per inch squared, which is PSI. So pressure is a measure of the gas particles' collisions with the side of the container as in measured, and we're going to cover these. This is millimeters of mercury, it's mmHg or torr. Atmospheres, ATM. Pascals is PA, or kilopascals is kPa, and pounds per square inch is PSI. So we are not aware of the pressure. We rarely pay attention to the pressure around us. Unless, of course, one of the biggest ways that you're aware where that pressure exists is when your ears start popping. That's when you're aware that there is pressure going on, something's going on around you. But for the most part, we have been accustomed to the pressure. We have molecules hitting our body constantly, and we are so adjusted to it, we don't even feel what's happening, this pressure on the outside, that we're being bombarded nonstop with molecules. So the atmospheric pressure, it comes down on us, and what is atmospheric pressure? What's the molecules that are in the air? So it makes up of oxygen, it's nitrogen, and then other gases, and depending on where you are, even water vapor. So the atmospheric pressure, it is at 1 atm at sea level, and anything you can get an idea of where something's located based on knowing that at sea level the pressure is 1 atm. So if you start increasing in altitude, the pressure is lower there, and that's because there's not as many molecules in the air as there are as you start getting into sea level. So even the air is thinner up there, so it's harder to breathe because you don't have as much oxygen available as you would at sea level. So the decrease as altitude increases. So if we look at this is a nice little depiction of what's going on. You have higher pressure the lower you go because you have more and more molecules, and they're bombarding you way more, but you don't feel it. But as you go up, you have lower and lower pressure because there's less molecules, meaning also less oxygen. That's why, these people that climb Mount Everest, they need to have oxygen. They wear those oxygen packs because there's not enough oxygen in the air unless they acclimate to it, and that can take a very long time. And even then, it can kill you if your body doesn't acclimate to it. So the higher you go, the less oxygen you have, the less molecules that are up there, and the lower the pressure. So here's another idea to give you. So if you know that sea level is 1 atm, it's also equal to 760 millimeters mercury. So anything that's lower than that you can see is above sea level, and anything below that is below sea level, which has more molecules bombarding you. And Mount Everest, you can see, is a very small value compared to what would be at sea level. So there's not a lot of air molecules in the air as you increase in altitude. So let's go back to the straw. So again, what I told you is that the pressure, if anything's open to the environment, then it has the same pressure everywhere. However, once you start drinking through the straw, you change the pressure inside here because you suck up some of the molecules that are in it. So you're lowering the air pressure, which means that you have a pressure difference. And out here, the pressure is higher than it is in here. So this actually presses down and allows this liquid to be sucked up through the straw. So now that we've covered 7.1, this is 7.2, 11.2, sorry. We are now going to look at the kinetic molecular theory, a model for gases. So this is a theory to understand the behavior of gases. Now there's a few things you should understand about this. It predicts the behavior of most gases under certain conditions. So that's the key, under certain conditions. And there's assumptions that are made to understand this kinetic molecular theory. So let's take a look at, but it does work pretty well for the most part to understand what's happening. So the kinetic molecular theory collection of particles in constant motion. They never stop moving. They will keep moving no matter what. Even if they collide, they turn around and they keep moving at a high velocity in the other direction. There are no attractions or repulsions between particles. Collisions are like billiard balls. So pool table, if they hit, they just keep going in the opposite direction. They're not attracted to each other. In reality, this is an assumption that we don't acknowledge because the value could be so negligible that we don't have to consider it. But there is some slight attraction and repulsion between them, but we just take it as there is none. There's a lot of space between the particles compared to the size of the particles themselves. So what this means is there's a lot of dead or empty volume compared to the gas particles themselves. So that's why a gas can be compressible, because there's so much empty space that you can actually push them together, where you can't do that with a solid and you can't do that with a liquid. The speed of the particles increases with increasing temperature. So the speed of the particles is also directly proportional to the temperature. If the temperature increases, then the molecules will also increase. If the temperature decreases, the molecule speed will also decrease. This just gives a better description. This is from another of my classes. A gas is a collection of particles in constant straight line motion. Gas particles do not attract or repel each other. They do not interact. There's a lot of space between particles compared with the size of the particles themselves. And the average kinetic energy. Now this is average. What that means is that, remember, average is there's some above and some below. So the average kinetic energy of all the molecules in a certain space, the energy is due to the gas particles is proportional to the temperature in Kelvin. So we're going to be working in kelvins. When you deal with gases, we deal with Kelvin. We only deal with Kelvin. So we move everything out of Celsius into Kelvin. And as the temperature increases, the particles move faster and therefore have more energy. So this again is another slide that went with the other one. It's just more descriptive of what I was saying. I meant to remove this. Okay, so kinetic molecular theory is consistent with the properties of gases. Gases are compressible. That's because they have a lot of volume between them to avoid them interacting with each other. And they are very fast and very... So think about somebody who walks in a room with perfume. If you're on the other side of the room, you'll still smell that perfume because the gas molecules move at such a high velocity that eventually you're going to smell you're going to catch that perfume. But the person wearing perfume, all those gas molecules are going in all directions until they hit some resistance, and then they just go back in the other direction. Gases assume the shape and volume of their container. Gases have low densities in comparison with liquids and solids. They have very low densities compared to what liquids and solids have. Gases are compressible. Again, that's because the volume in between them is so large that you can compress a gas where you can't do that with a liquid. You might be able to do a little bit, but you cannot do more than that. You'll get resistance and then it just won't happen. A gas assumes the shape of the container. Whatever container a gas is held, it will completely envelop, it will completely fill that container because of the fact that it moves at such a high speed. It's going to keep going until it hits resistance. Again, and since the attractions between molecules in the gas are negligible, so yes, there is some attraction and repulsion, but at this point we just ignore that. We pretend that doesn't happen. And gases have low densities. They have to, because they have to be very light and they have to be able to move very quickly. So they don't have the densities of something that's very heavy in comparison with solids and liquids. So there's a lot of empty space between them. So if a liquid in 350 ml or 12 ounce can of soda was converted to steam, which is gaseous water vapor, the steam would occupy a volume of 595 liters, the equivalent of 1,700 soda cans. The density of steam at 1 atm pressure and 100 degrees Celsius is about 0.000, I think I said too many zeros, 6 grams per centimeter square. So if we convert this liquid to a gas, it would have to take us 1,700 cans of soda just to contain that gas now that's held as a liquid in 1 can of soda. So this gives you an idea of just how low and dense and how very few particles are in gas compared to something that would be converted to soda. That's it.